Good evening. Thank you for joining us. My name is Laura Heisler. I'm Director of Programming at the Wisconsin Alumni Research Foundation and the Morgridge Institute for Research, which are two of the three organizations in this building, the other being the Wisconsin Institute for Discovery. And the three organizations have come together to create this Crossroads of Ideas series. And we got the name from the idea of this town center that you're in, because when we built this building, we really wanted this space to be a crossroads of ideas across the campus and connecting people who live in Madison with the research that goes on campus. And we have tried to bring you topics that are important in all of our lives that also happen to be the subject of research here at UW-Madison. And so that's what this series is all about. It runs typically once a month on a Tuesday evening. We had to cancel our last one because we had a freak snowstorm, not the one last week, but the one earlier in April. And so we do have one more talk that rounds out the semester, and I'll mention that in just a moment. But I did want to give you a couple of notes about how things are going to proceed and what you can expect. So our lecturer will talk for about 40 minutes or so and then open up the floor to your questions. We do videotape all of these sessions, and so we ask that if you have a question that you raise your hand, and we will have a mic runner come to you with a mic, and that way we capture your question on the videotape and everybody's happy. The videotapes the links will be live. We don't use videotape anymore. The links will be live on the discovery.wis.edu website in a couple of days if you want to revisit them or look at any of the other sessions that we've had this year and over the last couple of years. I also want to mention that tonight's speaker, like a speaker that we had earlier this semester, is one of the first recipients of a new initiative that is a partnership between Wharf and UW-Madison called the Uw Wharf 2020 Initiative, which aims to create really groundbreaking research in high-impact, high-risk areas. And I'm just going to read a statement about the goal of the 2020 initiative, which is to stimulate and support highly innovative and groundbreaking research at UW-Madison over the next 5 years. The initiative seeks to fund research projects that have the potential to fundamentally transform a field of study, as well as projects that require significant development prior to the submission of applications for external funding. So the idea is to seed whole new avenues of inquiry in really high-impact, high-risk areas. It also works on the acquisition of new instrumentation that can be transformative for a lot of different research at UW-Madison. So that's Suman Banerjee was one of the first recipients of a 2020 award, and we're beginning to get to that first wave of projects that are coming to fruition now. So it's very exciting for us at Wharf to be able to feature his talk tonight. A little bit about Professor Banerjee. He received his PhD in computer science from the University of Maryland in 2003 and joined the faculty of UW-Madison right after that. He's the winner of the ACM SIG Mobile Rockstar Award in 2013, so a bona fide rock star, awarded for early career achievements in the field of mobile computing and wireless networking. And he's currently serving as chair of the ACM SIG Mobile Committee. He received an NSF Career Award in 2008 and leads the Wisconsin Wireless and Networking Systems Laboratory. Research in this lab, known as WINGS, is conducted in the areas of networking and distributed systems with a primary focus on wireless and mobile networking. And a significant focus of his current research is in mobile computing and wireless networking. And he will be talking to us about the era of edge computing. And before I turn things over to Suman, I just mentioned the final talk in our series is next week. This was one we had to move because of the snow. In honor of the bicentennial of Frankenstein, we will be talking about human head transplantation with Professor Susan Lederer from the Department of Medical and Bioethics. Human head transplantation is a thing, and there's actually been some news recently about facial transplantation, so you might want to come to this one as well on May 1st. And with that, I am delighted to turn things over to Professor Banerjee.
So good evening, everybody, and it's a pleasure for me to be here and be able to share with you a little bit of some of the things that I'm doing. I called my talk Riding the Next Wireless Wave, and it so happened when I put together the title, this was not really planned, but it turned out that last week, am I going the right way? Last week I was actually in Hawaii, and I was trying to really ride the wave, but it's fun to come and talk about something else, which is also a big wave, and good to come back to great weather in Madison. So I want to tell you a little bit about what's happening broadly in this very exciting space on mobile and wireless networking research. All of you are probably users of some kind of a mobile or a wireless device. So what I tell you today, some of it probably is not new, but I think the numbers are pretty astounding. And I think where we are going, I think requires a lot of thought and a lot of effort in order to deliver what we continue to expect from these wireless and mobile systems that we are so used to today. Okay? So if you look at various statistics, wireless systems are just continuing to explode. There is predictions, different predictions by different entities. Companies like Cisco, of course, want to predict that things are always going to grow and do better, but they base it on real numbers, real trajectories of how things evolve. And one of the things they actually predict that by 2021, which is barely 3 years from now, 63% of all internet traffic will come from wireless devices. This is actually astounding. It's almost like 2/3 of all internet traffic will be from mobile or wireless devices. The number of connected devices in the world will be 3 times the human population by 2021. Okay? And actually, I think this is, in my opinion, a little bit of a conservative estimate, maybe because it's only 3 years out. What's going to happen is, of course, probably people already own 3 devices. You have a phone, you have a laptop, maybe you have a tablet, that's already 3 devices. There's going to be tons of devices that will connect light bulbs, and people joke about your toaster being connected to the internet and lots of other devices being connected to the internet. The number of devices will definitely explode, and the number of, it will be far more than the number of people in the world. That's kind of something pretty unexpected when the internet actually started out, right? In fact, the number, I think the estimate is like 27 billion. So by 2021, we may have 9 billion people. I don't know if that's right, but that's sort of the estimate that Cisco has in the number of connected devices. And most of these devices will connect wirelessly. Okay, that's large, a really large number of devices. And the growth is, the number I said is 63%, but I think what is amazing is that the growth is incredible. This is another chart. I think this was generated by Bloomberg Finance. And they essentially predict that going from 2016 to 2021, this is the amount of traffic in units called exabytes, right? You've probably heard of megabytes and gigabytes, and then there's terabytes, and you keep going, petabytes and exabytes. Okay, just think of it as a very large number. And that volume in 5 years would have grown by a factor of 7. Okay? To us, it may seem like just a number. Okay, you went from 7 exabytes per month to 49 exabytes per month. What's the big deal? Think about other things that we do, and if it went up by a factor of 7. So for example, think of cars on the road. Okay? This is a chart of how vehicles are going to grow over the next, 25 years, starting from 2015. From 2015 to 2021, it grows by maybe 30–40% at most. Okay? If the number of cars on the road went up by a factor of 7, you would have to really rethink what's going on. But that's what we expect of the mobile internet. Okay, so it's really astounding. We take it for granted. It's been going on for a while, and we take it for granted. But it really requires new thought on how to support that growth. The infrastructure that is required to support that growth is not easy. And just as if the number of cars on the road went up by a factor of 7, we will be in a huge crisis. And that crisis is a daily factor in the research domain of mobile and wireless systems. So the question that we posed, and broadly a lot of people in this broad community is thinking, is if you think a decade out, so today is 2018, if you think out 2028, right? I said in 5 years we'll be up by a factor of 7. If the same thing continues, we may be up by a factor of 50 or 100, who knows what that number will be. That's already a challenge. But a bigger question to ask is this big data tsunami that's coming our way, is it more of just the same? Is it the same kind of things we continue to do today? Or are there more complexities that we need to worry about? Okay, so just think 10 years out. And it's, again, a very hard question. I don't have a clear answer. But perhaps a way to think about how hard it might be in 10 years is to think back 10 years. Okay, so roughly, instead of going to 2008, I went to 2007, a very convenient year for us. In 2007, early part of the year, the state of the art in mobile technology was these devices. Now, I'm sure some of you may recognize them because you may have used them. These are flip phones, and they were really, really exciting technology of the time. Nokia was probably the leader of the time. And we could do a bunch of things. We could type out text messages, we could do some web browsing. And then Steve Jobs came and introduced this other device that really became the genesis of the smartphone. Right? He went and said, this changes everything, and he waved his hands, and everybody was excited. And truly, it was a device that transformed how mobile internet interactions happened in the world. That was 10 years back. So in 2007, before the iPhone came, if people asked you, what do you do in the mobile internet? The answers you'll probably get are very different. And it changed within about a few months after. And if you think of sort of the decade that has gone by since 2007, it has really exploded. There are lots of wireless enabled gadgets out there today that was almost unimaginable in the beginning of 2007. So here are a few examples. There's this Nest thermostat that sits in people's homes and controls your furnace and does all kinds of things. Has a very cool interface. You can program it from your phone. You can tell it what, it can probably tell when you're gone. It will do certain things for you. There is this light bulbs that are on the internet by Philips. There are other companies that make such light bulbs. You can program it to change its color based on lots of things. It can change its colors on a pattern. It can do all kinds of interesting things. There are devices that detect, there are smoke alarm detectors that are connected to the internet. There are speakers that are connected to the internet. You can have a device, a speaker is sitting there, and it's connected to an internet radio station, and you press a button and the internet radio starts streaming in your home. Of course, there are smartwatches that keeps track of all kinds of things about you, about your health, and other kinds of gadgets that does similar things. There are things what are called VR headsets, virtual reality headsets, that can literally transform you to a different world. So these are all the things that have just happened in sort of the last decade and have really become practical and usable in the last decade. Okay? So now, if you want to think of what can happen in 10 years in this world, I think it's pretty fascinating. And it's really almost scary for people who are going to have to deliver that service, right? People can dream up all these fancy applications and systems, but then have to give that performance so that people can use it. In 10 years, things can completely change. So I think if honestly, if you ask a technologist, most of them are very bad at predicting what will happen, okay? But you can see some examples of what is slightly beginning to happen, and it's pretty mind-boggling. There is this beautiful internet video that you can check. That picture over there, it's very weird. I don't know if you can tell. That's basically a basketball court, and people are watching a basketball game. And they created this mixed reality environment where this whale comes and jumps into and goes away. And you should actually see that video, and people get shocked. It's so real because they were able to recreate this using various ways of communicating this information and displaying this to people. Okay? And this is a technology, there are different forms of it. There is augmented reality, virtual reality, mixed reality. Essentially, it makes you sort of feel that you're in a different environment and gives you almost the real-time interaction of being in a different environment. There is lots of applications. You could be a doctor who's transformed to a surgery location and you're actually physically helping with a real surgery. Lives depend on that. You could be a student who's transformed to maybe Egypt and you're really experiencing the pyramids or the Sphinx or anything else and gives you a real sense. So all of these capabilities are enabled by things like virtual reality, augmented reality, and so on. There are obviously implantable devices. I know people sometimes get a little queasy about having things in their body, but there's a company, I believe, in Wisconsin that has started doing some of this. And there are others that will eventually follow suit, and it can transform our understanding of our health and physical fitness and all of that. And of course, we hear about autonomous vehicles and the need for these vehicles to communicate with other vehicles, to the infrastructure, to be aware of what's going on in the world. So this is already sort of happening. What can happen in 10 years is unknown, but I think it can be sort of unbelievable from today's standpoint. So I think that future technologies like this can almost be like science fiction today. Right? You see movies like Minority Report and others, and truly, though some of those things can be realized in a period of 10 years, I think that is not so outrageous to think. So to having seen this, having seen the growth in the last 10 years, and looking at how this field is poised, a lot of us, myself included, but there is a lot of leadership in the federal government, in the National Science Foundation and other organizations, they've realized that if the technology is to move this fast, you need an infrastructure to support it. Right? Today we have certain infrastructure, you use your cell phones, you're happy with it perhaps, you can browse things, but some of these applications I'm talking about will need far superior resources and capabilities from an infrastructure. And so to meet these goals, organizations like the National Science Foundation recently have, with participation of the broad community, including folks like myself, announced this big initiative. They call it POWER, which stands for Platforms for Advanced Wireless Research. And what they are encouraging the community to do, community here being the wireless research community, to come up with platforms or test beds or infrastructure that will encourage such innovations, encourage ways that will allow people to build innovative wireless technologies that will support this high bandwidth and low latency and exciting applications, and enable it in large scale to demonstrate that this can actually work in large scale. Okay? So in fact, one of the objectives of this initiative from NSF, for example, is what they call a city-scale wireless infrastructure. Infrastructure that you can deploy across a city. It's experimental in nature, and you can try new things on it. Okay, it's a very bold initiative, and they have launched this program, and they are encouraging cities and universities to lead such efforts at a city scale. In fact, this was launched back in 2016 by the previous administration, and they allocated a huge amount of money to support such initiatives. Okay, in fact, the launch happened in the White House, and I was there, and with a lot of other people, and there's a lot of excitement in making sure that the US stays in the forefront of this very important technological area. Otherwise, it would not be good to fall behind. So the very goal of this initiative is to essentially find a path to bridge what is sometimes called the valley of death. What is the valley of death? So let's say we do some research in the university. We come up with some smart ideas. Maybe many times we come up with bad ideas, but once in a while we come up with a few smart ideas. The challenge is those smart ideas may not immediately be commercially viable. Okay, they may not turn into real products. They may not really be cost effective or something. And sometimes it is because we built something, but we could not demonstrate that it works at scale. Right? I have 2 lab prototypes. I can do a little thing. But does it work when there are thousands of users or hundreds of thousands of users? Nobody knows. Nobody wants to take the risk of taking it from the lab prototype to the commercial deployment. So it dies for a while until somebody figures out a way to look at it again, and maybe a successful company then picks it up and becomes a successful company and then moves on. But there's a big gap. And the goal of this initiative is to come up with a way to bridge that valley so that the researchers, whoever came up with that idea, can transition the technology faster to a real, usable, practical system. So that's what NSF and a lot of federal agencies have been proposing. And so a lot of us, a lot of cities, a lot of communities, NSF doesn't, they use the term community instead of a city because they don't want to exclude rural communities, which is not a city. So they use the term communities. But a lot of communities have started looking at how to build a city-scale wireless infrastructure that supports research. We are familiar with a lot of city-scale infrastructure. You know, all the cellular operators have a city-scale infrastructure. They give us cell phones, and we have a cellular service. There are home ISPs that give us a city-scale infrastructure that give us home ISP services. This is meant to be an experimental infrastructure to support innovation. So if I come up with a smart idea, or you come up with a smart idea of how to give 100 gigabit per second to your phone, they should be able to test it on this infrastructure. So they want us to build infrastructure that's at city scale to experiment with these ideas and showcase how innovations can be deployed on this infrastructure. So my UW 2020 project that Laura explained is actually focused on turning Madison into a city-scale infrastructure of this nature that we can build, and with NSF's help, we can grow and create a viable and exciting environment in our city, in our hometown here, and do bigger things that we can do otherwise today. So the infrastructure that we are planning, obviously, is at city scale. We are already in deep conversations with our city, but with many other stakeholders. We are working with our local bus operator, Madison Metro. We are looking at deploying lots of hardware across different locations in the city. I'll talk about it in a second. And we are trying to engage with real users in certain way so that if a new idea comes in, we can pilot it in Madison. Okay? What those ideas are, I'll give you a few examples, but really it's up to us and other researchers to come up with these ideas and deploy it and show how useful they might be. Okay? So I'll give you what kind of research you can do if you had an infrastructure like this. If I had an experimental infrastructure spanning a whole city, you could, for example, here is an experiment you can do. I'll give you a couple of examples, both from the vehicular domain, because that's sort of an area we are focusing on in Madison. You know, we all hear about autonomous vehicles, right? They are all the rage, and they also have all kinds of problems. There are incidents that come up now and then which doesn't make us feel very comfortable that they can be successful and they can be dangerous. And if you look at all the deployments of autonomous vehicles today, they're in very controlled environments in the sense that they would have, you know, say Google did it or Uber did it. They went and really collected a lot of data about what the environment looks like. They took lots of pictures and videos, analyzed it to depth, and then deployed these vehicles because they can match what they know about the environment to what they observe, and they can do certain things, which is how these systems have evolved. But imagine, I mean, so this is of course the first step, but autonomous vehicles are not easy, right? It's very complex. It's a very complex environment. You have pedestrians, you have bicyclists, you have other vehicles, and sometimes people are trying to check if the autonomous vehicle can do the right thing and mess with it, really, right? So it's not easy. And imagine in Madison, you know, you tested a bunch of things, you did it well, and suddenly it starts snowing, and you did not have enough models of snow and ice and sleet and other things. How will this system react, right? Of course, if you come up with a technique to do that, I won't deploy it on the city right away. We'll have to go through all kinds of testing. But eventually, we would want to have a very controlled environment where you can track the vehicles, you can communicate with the vehicles. If the vehicle has a problem, maybe somebody can remotely take over the vehicle, right? Without that, it's very dangerous, or maybe stop the vehicle. So an infrastructure of this nature can allow us to at least run controlled experiments of this type, okay, with obviously the appropriate checks and balances in place. I'll give you a more simpler example. Imagine for a second that every, say, city bus has a lot of cameras. They actually already have. All city buses have, I think, 6 to 8 cameras, mostly for responding to incidents. Something bad happened, they can look at the images and say, okay, this is whose fault and what happened. But imagine that I could use that same camera data and do something more. As the buses are going by the roads, I can look at where are the parking spots that are available right now, provide it to a broad class of users, and they can immediately say, okay, there is 3 spots on the, this corner of University Avenue, or in downtown or around the square, and I can probably try and utilize those spots as opposed to keep circling around trying to figure out where the parking is. This is a relatively sort of cheap way of gathering parking data. Today, if you actually want to know where the parking spots are, you have to put sensors, and you have to have a full other infrastructure. Here, all I'm doing is I'm leveraging cameras on city buses to figure out where the parking spots might be. Okay, these are just pie in the sky ideas. You might have 20 other ideas of doing something more interesting with the data. You could say, how about I use the cameras to figure out, are the traffic lights operating well? They stay green and red for a certain duration. Is it actually the right amount? Should it be changed? And can I provide evidence that the traffic system should have updated the durations of red and green differently, right? So you can do all kinds of interesting things. And with an infrastructure that is city scale, that allows you to send data out to the cloud and bring some information back to the vehicles, you can actually run experiments of this nature and come up with some interesting solutions. Okay, so that is the goal of our UW 2020 project, is to study and build experiments at city scale, really spanning a large part of the city, and in fact greater Madison, not just Madison, it includes Monona, and we will probably get into other neighboring parts of Madison. This map essentially says our plan is to deploy a lot of things. They're all wireless nodes doing different things. I'll explain a little bit more about what they do. But they will be all future looking. They will be technology that can operate at some capabilities that are not possible today. That's what the research or the experimentation is about. They might operate at tens of gigabits per second, or they may operate at so high speeds that you can run experiments that are not possible today. Okay, so it's taking a research lab and putting it out across the whole city, and in turn, it will also try and benefit the city because we can roll out new services in Madison that are not easy otherwise without some infrastructure of this nature. So let me tell you a little bit about the kind of research we are thinking of. If you think of a lot of wireless research and activities in the past, it has mostly been about faster speeds. And by faster speeds, I mean bandwidth, right? You see the numbers, you see these things called 2G, and then 3G, and then 4G, and there is 5G coming, and there'll be a 6G, or maybe a 10G. Essentially, G stands for generation. And as you go from one generation to the next, you go up significantly in data speeds, right? You used to have hundreds of kilobits per second in 2G, 3G gave you a megabit per second or so, and then 4G is tens of megabits per second, 5G claims higher speeds. It's all about the speed, how many bits per second you can send, how fast you can send data back and forth. So that is one important measure of performance. But some of the applications I showed you, where you're talking about virtual reality, and you're talking about autonomous vehicles talking to roadside things, is not just about how many bits you can get per second. That's data rate or speed is not the only metric. One of the important requirements in the future for a lot of these new applications, imagine you're doing telesurgery, right? A doctor is communicating to a remote system that's actually operating on a person. One of the things that matters a lot there is latency, the time it takes for one bit of data to get from the doctor's station to the remote site. It's not how many bits I can send simultaneously. It's how long does it take for that single bit, the first bit, to get to the destination. Okay? Lives will depend on that latency. So latency is actually a very important thing. Reliability, we sort of sometimes neglect that in the wireless side of things, right? I mean, we are used to, okay, the Wi-Fi is not working right now, let's shut it down, start again, it works now. That's not reliability, right? We are used to reliable networks when we are on the wired side, right? If you're on a computer, we almost expect nothing to fail. If it's Ethernet connected or in your desktop in the office. On a phone, yeah, the phone call may drop. You can have other issues. These systems have not always been designed with the most reliable ways of accomplishing these goals. This will become critical. Somebody actually put it actually very nicely, saying that we want the next generation of wireless networks to be systems on which we can depend on which critical services can depend on. Today, they're not truly that. Things fail more than that they need to be. Okay? High bandwidth will still be important, but there are other things that are going to be significantly more important. Low latency, high reliability. If you think of latencies, latency being the time it takes for the first bit of any message to go from the source to a destination. Let's say we're in Madison. If you want to go to the West Coast, on the internet it may be 50 milliseconds. It can be lower depending on which networks you traverse. If you go to Europe, it's 100 milliseconds. If you go to Australia, for example, it doesn't go that way. It actually goes the other way, but there was no easy way to show that. It could be 300 milliseconds. Okay, that's just latency on wired systems. There's no wireless in this picture on the three numbers I put up over there. Okay, if you are using a cellular link, depending on what you're using, you can easily add another 50 to 100 milliseconds to it. Okay, just for your phone to send data to the nearest cellular tower and to a nearest exit point into the internet, that takes another 50 to 100 milliseconds on top of these numbers. Okay, so that says you are at least 100 plus milliseconds, maybe 200 plus milliseconds. That's not good enough. If you're doing this virtual reality application where you're trying to interact with something and you're in a different environment, the latency requirements are of the order of a few milliseconds. Okay, if you have a higher than that latency and you're wearing this headset and you think you're in a different world, you'll get nauseous. Okay, that won't be pretty. So latency is very problematic, and the challenge is, of course, there is this one universal law that limits how fast you can do certain things, which is speed of light. Going coast to coast in the US is about 13 milliseconds. You can't go faster than that unless you can somehow break the speed of light, which you cannot. Okay, so this is an issue, and for a lot of these applications, that's one of the major things you have to actually address. How do you build a system that can give you this very low latency performance so that you can implement these other applications today? There's a lot of applications. So this is actually a chart that has, on one axis, the x-axis, you have throughput or bandwidth. Goes from a megabit per second to a gigabit per second. On the other axis is latency or delay. It goes from 1 second to 1 millisecond. And it shows where different applications sit. So for example, if you're doing video streaming, right, you want about 10 to 50 megabits of megabits per second video, and you can live with a second of delay. It doesn't matter. Watching a Netflix movie, yeah, I can start my movie a few seconds late, but then I get to see the nice experience, and that's fine. As you go up in that right top corner direction, you get to these applications that really require both high bandwidth and low latency. And the examples there are autonomous driving and all these virtual reality, augmented reality type applications. And broadly, the term people use is tactile internet, where you're trying to do something and you expect the environment to get back to you in real time. And that's where you need all these 1 millisecond type delays. Okay, you may think that it is a small number, but it's actually very hard to get that small number for interactions between users and some infrastructure. Okay, so that's what one of the challenges I think this kind of a city scale infrastructure should try to address, is to encourage innovation that gets us in that top corner over there, which is high speed and low latency. It's a very hard thing to accomplish. And as I said, applications like virtual reality, and in fact, there's another term now called virtual presence. You want to virtually be somewhere else. You really want to feel that you're part of that environment, slightly more than virtual reality. Almost feel like you're physically in a concert when you're not there. And there, if you have anything more than a few milliseconds of delay, it's not acceptable. Okay, so building the technologies that support this is going to be a big need and the demand really of users in the next decade. And that brings me to the point, little bit of today's talk, the concept of edge computing. This is actually a big innovation that's happening worldwide now, and we are deeply involved in this. What is edge computing? We all know what is cloud computing, perhaps, right? You have these data centers that sit somewhere, we don't know where, we don't care where they are. We call them the cloud, and essentially this is some organization like Microsoft or Amazon, they manage these things. They have these huge racks of servers and cooling systems and all kinds of infrastructure, and that's where this computing capabilities reside, right? So if I develop some smart application, my server will reside in Amazon cloud or Azure cloud. It's Amazon or Azure's problem to make sure the servers are always running and they're powered properly and cooled properly and nothing fails. So it reduces my burden of running this service, and it makes my life a lot easier. They are centralized and in a few sparse locations around the world, not everywhere. Madison may not have a huge data center, it may have a small one, but not a huge one. And there are a few places in the world where these things are located. Edge computing is the concept that says, well, if you did just that, your computing is going to be 100 plus milliseconds away from your end users, right? We looked at that slide which said you have a 50 plus millisecond delay plus another 50 if you have a 3G or a 4G network. So you have a large delay from end users, and that is not going to work for a bunch of applications. Why not create this mini clouds in what we call edge networks that are closer to end users? Okay, and that is what's called edge computing. How this is managed and organized is a very interesting question, and what I will talk to you about is a form of edge computing that we are working on. It's what I call edge computing in the extreme. Okay, what is edge computing? It's bringing computing capabilities close to the edge. What is the extreme edge of the internet infrastructure? If you think of, data centers in the cloud, then you have all these routers and switches somewhere in the cloud, different networks, and you keep going. Eventually, something comes into your home, some cable line comes into your home, and then there is a box. Usually, that box is a Wi-Fi router. That is actually a computer. We don't think of it as a computer, but it is a computer. Of course, its main job is to send you Wi-Fi packets and receive Wi-Fi packets, send it to the internet and so on. But it is a computer, and what we have been trying to do is to take that Wi-Fi router and treat it like a computer and turn it into a mini cloud in your home. Okay, sounds a little crazy, but it actually can be done. It is a computing platform. You can run services there just like you run services in the Amazon cloud or in Azure cloud. Okay, just like you run things in Microsoft and Amazon, you can run certain things. You can't run the same capabilities. It is obviously weaker, but you can run a bunch of things and you can make this more capable based on what you need. Okay, so we have been doing this project of edge computing where we take this Wi-Fi router and turn it into a compute platform along with, of course, doing its Wi-Fi tasks. And it's interesting because it enables a large number of smart home applications as an example. So for example, today there are things like Nest, and you can imagine implementing an application where you say, okay, I want to implement a smart heating system in my home. And the way this will work is it will sense if I'm in a particular room, and if I'm not in the room, it may shut off my vents. If I'm in the room, it'll open the vents and it'll try and change my settings so that the temperature is right for me. And when another person is in that room, it'll change the settings so that it's right for that person. Okay, so if you want to implement a system like this, what you need to do is you have to collect a lot of this sensor data. You have to decide what settings you should implement, and you send back those decisions back to the vents or whatever other devices you have in the room. Where does that compute function happen? Today, it has to happen in the cloud because there's nowhere else to do this, right? Nobody else. If I'm a third-party developer that came up with this idea, I cannot do it anywhere else. I will instantiate a cloud instance and I'll take all this sensor data to the cloud, And there I do the computation and say, okay, now change that vent to off and on and turn this fan on. I can do all kinds of stuff, but it all goes back to some cloud. But really, why does it have to go to somebody's cloud? It doesn't need to. I'm wasting a lot of bandwidth and it's not necessary. So instead, you could imagine running that simple logic on the Wi-Fi router in an environment that looks like the cloud. Okay. Another example is, there are systems that do monitoring in the home, right? You have cameras that are looking inside the home and looking outside the home, and they are trying to detect if there's an intruder. Maybe it's trying to be a nanny cam and check if your baby is crying, and then send you an alert, right? And what these systems do is all your home video, most of it is uninteresting, is streamed to the cloud. Gigabytes of data going every day. Of course, it's using up a lot of bandwidth that you don't need to. And I don't personally feel very comfortable that my home video is going to somebody's cloud, right? So it's a privacy issue too. There's no need for it to do that. I could essentially run the same computation. There's some computation that needs to happen. The computation is to look at the video and figure out, is there an intruder? Is the kid crying? Is something's going on? And then send an alert. That thing can run in your home router. I then eliminate all the need for sending this traffic to the cloud, and I run this locally on the home router. Okay? So these are some examples, just examples, but you can build more of these types of things that makes it very interesting to keep data local and not use a lot of unnecessary bandwidth in the internet, and give you a very low latency experience for different applications because it's running locally. Similarly, you can imagine that, let's say a student is sick today, couldn't come to class, but wants to, say there was a big video demo that was going on about whales in some ocean, and they want to wear this VR headset, sit at home, and get that experience from a cloud server. Again, if you run it from a cloud server, you will have that problem of being nauseous, right? If you're 100 milliseconds away from a source of this VR stream, the problem that happens, I turn my head. The moment I turn my head, what my human brain expects is the scenery will change with me. But if the data is coming from a cloud server, the fact that I turn my head has to be told to the cloud server, and that guy then has to send me the new data. That if it takes more than 100 milliseconds, my brain will get confused, and that's what causes people to get nauseous. Okay? It cannot therefore come from the cloud server. You have to do something local. So again, your Wi-Fi router, if you equip it with the right software, can be the local source for doing this kind of a stream. So there is lots of examples. So these are home examples. You can also do vehicular examples. So if I wanted to implement that system that does this parking finder, I can set up this router to be in the vehicle. I can set up cameras, and it does the same thing. It processes the video from the cameras to identify the parking spots and sends it out to the cloud so that others can therefore find out where these locations are. Okay? So there's lots of applications of this edge computing idea that I've been working on with our team here in Madison. We implemented, just to give you one more teaser example, we implemented a specific version of this system for one specific example. Okay? And the example we had was to understand how well people drive. Okay? I think I drive well, but the reality could be completely different. Okay? We have all these scenarios where people are fighting and shouting, perhaps a little less in Madison, but go to New York, Los Angeles, you'll probably see this more a whole lot. And we may laugh at this a little bit, and there are sad incidents. There was a really sad incident a couple of years back in Chattanooga where a school bus overturned and a few kids were killed, and it was just because the driver was driving badly. And the thing is, there are systems that could be built that can analyze how you are driving in real time. And that requires compute capability locally in the vehicle. So for example, by looking at how you are changing lanes, how you're braking, how you're turning, how you're speeding, I can tell a lot about how you drive, and this can be done by local sensors on a vehicle and some computing that analyzes it. Okay? So we've been using this edge computing platform to build a system that monitors how we drive in real time. And it is a system that, for example, gives you a real-time report on how you're driving. It will tell you, okay, you brake too hard here, you did something weird here. It gives you all this information. Of course, it can be done better on how you display this information to the user. but it's a tool that can help users both improve their driving as well as understand, for a lot of commercial fleets, for example, they want to know how their drivers are doing, right? You see the stickers which says how's my driving, and you call a phone number. I don't think many people call phone numbers, but if you have an online system, you probably will get some real-time information, and that could be useful. So I'll not go into how we implement this. We use different sensors from mobile phones and collect data and do some analytics, and the key piece over there is this edge analytics. We have a compute platform that does this data collection and analytics to figure out how well you're driving. And one of the interesting things we have now is going beyond just the sensors that can tell you acceleration, brakes. Your mobile phone can also collect that data. We also now have started to use cameras, right? So to give you an example, imagine that I want to analyze how well you did on a left turn, right? So here is, if you've forgotten, I think all of you are really good at this, but if you don't remember, you should be checking your left mirror, right? You should see that the person looked at the mirror. You should check basically your blind spot. You should turn on your turn signal, and then you make the turn, right? If I have a camera and an audio sensor, I can verify if the driver did all these things, right? Of course, now you have cars that have a camera inside the vehicle, so maybe you don't have to look, you can look at the camera. So all kinds of things can be different, but I can come up with a way to do this. But this requires I have cameras on the vehicle that looks at the driver, looks at audio, whether the turn signal is on, and then analyzes and says, okay, your left turn was fantastic, you did a beautiful left turn here. And so here is an example where we are making, say, a left turn or a right turn, and it's looking at your face and whether you made a turn, you turned your head, and looked at actually whether the vehicle made a turn by looking at the angular speed of the vehicle, and looked at the different sides and gave you a good score or a bad score, right? So you can do this analytics, and again, to do this, you need this edge platform that will gather all this data, come up with a result, and tell you how well you did. Okay? Again, it's just an example. You can imagine building all kinds of analytics if you have these sensors and an edge platform that's sitting on a vehicle. So the platform we built, we call it Paradrop. I will not get into specific details on what this platform is. The only thing I will say is the name Paradrop, which I'm very proud of, is that it is, you can imagine you're paradropping these applications on demand into this Wi-Fi router. Okay, just like if I say, okay, I have a new idea. I really want to analyze how people, make right turns. Then I create a new Paradrop application, push it to that router, and it starts doing its work. That's sort of the system that we've developed. And we are very excited about this because we strongly believe, just like the iPhone came and transformed the mobile phone market, because now you can put apps on your phone, Paradrop is trying to do that for the Wi-Fi router. Maybe the Wi-Fi router is not as cool as a phone, but I think it can be very interesting because you can provide new capabilities and it can be very powerful. So with this as a building block, we are now trying to build this city-scale living laboratory where we're going to deploy lots of these Paradrop type routers on street poles, in vehicles. We are partnering with Madison Metro, for example, and our goal is eventually to deploy it in all the vehicles, on Madison Metro vehicles. We'll have some high power nodes on certain locations. We'll work with the city of Madison on a particular smart corridor where they want to do some interesting things with traffic analytics and traffic control. And that's something that there is a lot of opportunities for. We have already started doing some of these things in small scale, and it'll all be future looking. It'll all be technologies that today don't exist, but can potentially give us very low latency or very high bandwidth. There are some pretty pictures of things we are deploying now in some parts of the city. And we are very excited that we have done a few deployments with Madison's Metro buses to try out the feasibility of this. And one of the unique vehicles we have is a partnership with a company in Chicago that makes these tiny little vehicles. They call it the Dash. It's some of the text here is a little bit confused, but it's a company called Innova, and they make this vehicle which is 8.5 feet long. It's called the Innova Dash. They can brand it with our colors. It doesn't go very fast, no more than 30 miles an hour, and we can instrument it as much as we want. So any vehicular experiment we can think of, we can do it on this vehicle. And we have a lot of similar plans to build this in a greater scale across the city. And so our infrastructure we are building, we call it Mad Nest. It's a nest where you can put your ideas and see them grow, sometimes fail, and try it at a city scale. And we have lots of partners. We are working with, of course, the city of Madison and Monona. The mayors of both cities have been very supportive. Madison Metro, MGNE, AmFam, UW Health, and anybody here, if you have any ideas on what could be an exciting, future thinking, crazy idea that we could try out on an infrastructure like this, I would love to hear your ideas and see if there's a way to incorporate that. This is something that will go on for a few years. The UW 2020 project will run for another year, but our hope is that we'll get significant more funding through federal agencies and other entities, and this will be probably make us, the city of Madison and broader, to be really on the forefront of wireless innovations and research in the country and in the world. With that, I'll stop and thank you. I'll take any questions. Yes.
Are you getting pushback by like AT&T with the router and they're putting in fiber optics now and spending all this money?
That's a great question. So,
I was just curious.
no, so far, I think we are not big enough that we get that pushback. But the good news is that the program that, for example, the federal government has put together, they have a consortium of 30 plus companies that are actually supporting this effort. And there are companies like AT&T. I don't think AT&T is on it, but there are many companies like AT&T, and they do not see this as competition at all. We are not providing a service to really anybody. We are enabling people to try out new things. If the idea is good, then it will be commercialized. Then it will not be living on the experimental infrastructure. But this is to do something that you cannot do today. If you can do it today, it's not worth doing it on this infrastructure. So I do not expect anybody like AT&T to push back. And there are 30 plus companies that are part of this federal agency initiative that are actually helping us. They are providing more money, support, and equipment to make this infrastructure actually work. So I think that's not an issue. Yes?
A few years ago, Google was looking.
A few years ago, Google was looking for a city to wire and have pervasive network.
Absolutely.
And I think they chose someplace in Kansas and overlooked us. They were
Kansas
looking
City.
for a way to tie healthcare clinics together. And well, it seemed like we were a natural for that. We weren't selected. Would this pretty much produce what Google was talking about, or is it in some way different?
That's a great question. So I think Google's focus was, they have this, they call it Google Fiber. So they basically provide a fiber infrastructure to provide wired connectivity across large parts of a city. Kansas City is one of the Google Fiber cities. I think there may be one or two more. And what we are talking about is beyond Google Fiber's equivalent. So we are trying to do the wireless piece to be very high-speed wireless. So I think, Google's interest is, at least the Google Fiber project is more the wired infrastructure. We're looking at what is beyond wired. So it's complementary to something like Google Fiber. And to also let you know, there are fiber projects in the city, not perhaps as visible or as well known as Google Fiber, but there are projects that bring fiber to certain parts of the city. So I would say it's very complementary to something like Google Fiber. They don't focus on specifically wireless innovations. They're trying to get everybody to have a gigabit wired network in their homes. And so that's sort of the big difference. So, but it's complementary. If Google were to come here today, it'll still be very complementary.
I have a question about the framing of this
Okay.
set of initiatives as experiments. It's
Yes.
dangerous to be talking about experiments in the social media, social networking world. I know Facebook had an experiment a little while back in which the news feed was steered negative in some clients' accounts and positive in others, and all
Yes,
that.
yes.
And that really is off-putting and appears from a public relations perspective.
Absolutely.
Also, in terms of human subjects research, when does the facial movements and all of that and the focus on the driver get the human subjects boards involved? And again, a lot of experiment-related concerns.
Absolutely. So I think a big difference is a great point. I think companies like Facebook can do sometimes what they want based on whatever they say in their terms of service, which most people don't unfortunately read or don't have the reason to read. Luckily, place like here, university setting, we are a lot more careful and rigorous. You know, university has something called an institutional review board. They will have to approve any experiment that happens with university funding or federally funded research, and they have to give us guidelines, and we make up our plan, and they approve it or not approve it, and they suggest how we do things. So there's a very rigorous process in place. In fact, federal government will not fund us if we don't go through the IRB reviews. So we obviously will have to be careful, and these experiments, we will obviously, anybody who does it has to follow the same rules. So Facebook can get away with doing what they want to do. They still, I think, try to do something, but they're sometimes guided by their own business requirements and decisions. Our goal is to advance science, but we have to follow the rules of research practices and scientific practices. Thank you for that question. I think there was a hand here first, maybe.
Right here.
Okay.
I live in an area that has real low internet speeds. We live in a rural area and we're dependent on satellite.
Okay.
And I was wondering, when you were talking about the edge computing idea and having some cloud functions working in your router, would that help mitigate the slower internet speed?
I think it definitely can. I think, I should also admit that I'm not necessarily proposing a solution to anything specific. My goal is to create an infrastructure on which somebody else can come and say, I have this great idea that will give you high-speed internet in rural settings, and they can test it in our infrastructure. So there's a few things we are doing that are specifically research, but most of what I am interested in doing in this project is to create the infrastructure where somebody can have a great idea on how to solve that problem and they can test it better. So there are pieces like edge computing which can help mitigate low-speed internet in rural areas, but I think that alone is not sufficient. There are a lot of interesting wireless research going on that tries to bring gigabit speeds just over wireless, and that could be a solution for bringing high-speed internet in rural areas, because you may not have to deploy fiber to get the benefit of that. I know there were a few more. Yes.
This on? Oh, yeah. Knoxville, Tennessee, on 60 Minutes, it was supposed to be a model because they were providing cheap, government-based, free internet for the whole community, and that this was, that Obama thing suggests that we're ahead of other countries. That some people make the comment that we're behind other countries because they have much cheaper internet access, because they make it publicly available rather than privately available at much lower cost, and just make it universally available to the community. So that's the primary thing I want you to react to. But I'm also wondering, how does this compare to UW? Doesn't it have Wi-Fi in the buildings right now and everything? Is that something different, or something that would be more citywide in some way? What's different between that, what's happening at UW and at Knoxville?
Okay,
Yeah.
so maybe I'll comment on free Wi-Fi or government-provided Wi-Fi and what may happen in other countries. So I'm not talking about necessarily providing free Wi-Fi of any type. And I think, by the way, countries, people talk about countries that seem to have high-speed internet everywhere. Examples are places like South Korea, right? And I think it's very different in the US. US is far more challenging. If you think of South Korea, it's a very dense country. There is a huge concentration of population across a few urban centers. It's much cheaper to deliver very high-speed internet in that environment because it's easy to build that infrastructure at low cost. US is not the same. You have dense areas, you have sparse areas, you have rural, so much bigger, much broader space. So building cheap and efficient and high-speed internet across the country is a much harder problem. So it's not surprising that it's hard for us to match what South Korea can claim. They can claim gigabit speeds to every home. It's hard for the US to do that. So I think there's a gap. But I'm not talking about free versus not free. The technology, what you can do when you have the advantage of cost benefit because of density is different than what, say, the US can provide. So I think we still have to be at the forefront of innovation. The technology should, I believe, should always come from the US, and has been for the most part, and there are opportunities that are in front of us that we should take advantage of because of technologies that we can develop here. So that's one point. So I don't know specifically what Knoxville is doing with providing free internet, but whether it's free or paid, you have to find a technological solution to the problem, and then who pays for it is a different issue. Okay, that's the first thing. Second thing is about the Wi-Fi on campus. So Wi-Fi, if you think about it, does anybody have an idea what is the fastest speeds you can get on Wi-Fi today? You can probably get, most of the time you'll probably get tens of megabits per second if you're in a good environment, 10, 20, 50. If you're lucky, you can get 100, 200 megabits per second. That's today's Wi-Fi. Many times you'll probably get a few megabits per second. I'm talking about technology that may give you gigabits per second. So it's not even technology that exists today. Nobody builds it today. There are new technologies that are coming down the pipe that are likely to give us gigabits or tens of gigabits per second to your laptop, right? It doesn't exist in a very commercial setting today. So that's what we are trying to do, and we're trying to do this at scale, not in one building where I can put 50 access points and bring fiber everywhere, but in a city scale where I can do all of that as easily. So my goal is to build the technology that we will be obviously used to maybe 5 or 10 years from today, but we have no idea what that is today. I don't know if that answers some of your questions. Well, it's research, right? So, we get funded from the federal government to do the research. Once the research happens and the technology is demonstrated, somebody will build the prototype, will build the commercial product and will sell it, and we will all be using it. Just like the iPhone, the research that led to the iPhone happened in various places, not just in Apple. They build different things. Eventually, Apple built the actual product and are selling it, and others are doing it too. So I think that's actually a very long, the question deserves perhaps a much longer answer. Yeah.
This is a very interesting idea that you're describing today. Thank you very much. I think the genesis of where you're coming from is the fact that compute resources are becoming very cheap compared to networking resources such as bandwidth and latency, as you described. Now, we can imagine a time where there's fiber optics to a big fat fiber optic cable going to every single house everywhere. And then what are we limited by? It's the speed of light, as you said. We're not there yet, but it's possible that it could happen. And that would be great. And then you're coming at it from another angle with putting the compute resources at the local sites.
Yes.
Because they're so cheap. However, it seems to me there's going to be another limit in terms of what you can do with the applications because you're in an isolated cloud. So a lot of the applications that we're very happy with Google and so forth, it's because there's so many people, so much data from many different sources, and we're able to crunch all of that. So here you're really only getting data from a small number of sources, sensors, etc. So there's really going to be a limit to what you can do application-wise. What do you see? Where do you see that limit?
That's a great point. So I think maybe I should clarify when I'm saying that we should do computing at the edge. It does not eliminate the cloud. So it changes actually, and this is a little radical, it changes the computing paradigm. So today, if a developer comes up with an application, they create a mobile client, which they give to you as an app, and they create a cloud instance that sits in Amazon or Azure. In this new model, they will create three things. They'll create the mobile client, they'll create the cloud instance, and they'll create an edge instance. The edge instance will still talk to the cloud instance, and they can aggregate certain things in the cloud, but they don't have to send raw data to the cloud all the time. They can process it and do a bunch of things locally, and certain things which need to be pushed can go to the cloud. So you still, it depends on how you implement your service. But if you do it right, you do not lose any of the benefits of the cloud, but you gain the advantages of the edge. And it depends on individual applications. So I think it depends on the design, but it's actually a slightly different paradigm. I'm not eliminating the cloud, I'm adding an extra capability. I think I may maybe take one or two more questions. So you have somebody has a microphone over there.
The manufacturers of routers and Internet of Things devices have done a pretty horrible job of keeping them secure. And when you add more capabilities, it's hard to avoid making them even less secure. So I'm wondering what security components there are in your research.
Absolutely. So I think the core capability, and I will have to admit, I'm not a core security researcher, but I work with a lot of them. And the core capability is, so the technologies of securing things are all there. The challenge, the difficulties that come about are usually coming from how people engineer them, what policies they implement, and they forget certain things and things like that. So the main principal components we use are principles of virtualization, isolation, and a lot of capabilities that ensure that data that sits in one application cannot go to another application. It's all encrypted between two endpoints. However, I will not claim that what I'm designing is going to be perfectly secure. You know, person who writes a code can make a mistake. There can be software bugs. There can be vulnerabilities. You know, we use standard state-of-the-art security packages, but even they are attacked and vulnerabilities get detected. So, you know, this is an ongoing battle. I don't have a perfect answer for you, but at least we are aware of what are the right security tools you need to use. And perhaps a little advantage here is that because we have this local gateway in the home, for example, that can do certain things, instead of letting all these random devices try and do their own security and figure it out, I can do something more centralized, and I can be more careful about it in one location than rather than having to do it at 20 different locations, and each one can potentially make a mistake. So I don't think it answers your question, but I think we know what the issues are. It's still a research project, but I think the community knows what the right solutions are. Sometimes people don't apply it correctly, and that is the biggest problem. But you're absolutely right. You know, anything you introduce opens up new doors for attacking and hacking things. I think we have two questions, maybe. Go ahead. Okay. Maybe I'll take that as the last question then.
Urban areas like
Yes.
the city of Madison are comparable perhaps to South Korea. We have
Absolutely.
concentrated high density populations. I think it would be possible for us here in the city of Madison to replicate the kind of system that we
I think he's asking you to keep.
could we replicate the Korean service in Madison speeds?
Yeah, so the question is, are you able to replicate the, because we have densities in the urban centers in Madison, can we replicate the speeds and performance of, say, in a South Korean city? Absolutely we can. And I think showing that is probably interesting, but I think what is technically more challenging and what is more important is, can we then do something beyond it? Because that, if we solve it, nobody will say you did something fancy. Just because South Korea can do it doesn't mean they have a better solution. They can do it because they have the advantage of density. We don't have it. So I think the innovations that we want to go after is not just show that we can do it in the urban centers, which we can, but we can do it beyond the urban centers. And that would be a big win. That would really, actually is a very hard problem. And if we can solve it, is actually significant innovations and significant advancement of our technologies. But the short answer is, I think we can do that for what you asked for. I think if there is no other question, and given the time, I perhaps should close the conversation, but I'm happy to stick around and take any more questions if somebody wants to talk to me. Thank you very much.